In this video, I'll talk about power semiconductor devices, how to select such devices, and what kind of applications that are suitable for each one of them. And then we'll go and study the switch mode conversion in power electronic systems. Power semiconductor devices can be divided into three main categories. Number one is the uncontrolled devices. And these uncontrolled devices can include diodes, for example, the power diodes. Because, as you know, diodes don't use any signals to be on or off. We just use the flowing current. If there is current flowing within the circuit, the diode will be off, the diode will be on, and if there is no current, or if the current in the opposite direction, then the diode will be off. Number two is the semi-controlled devices. And these are the thyristors. We'll study this thyristor and we'll see how the thyristor is operating. We will know that the thyristor needs a signal to be on, but we cannot use any signal to switch off the thyristors. The thyristors will be off only if the current within the circuit became to zero, or if we apply reverse voltage across the thyristor, then it will be off. Otherwise, the thyristor will be on all the time. The third part, which is the fully controlled devices, and these are divided into two categories. Number one, the transistors. Such as BJTs, IGBTs, MOSFETs, and so on. Number two, the other type of thyristor, which is the controlled thyristor, the GTOs. Gate turn off thyristor. This type of thyristor can be categorized under the fully controlled devices. Let's talk briefly about each one of these devices and see how this device operates within the power electronics context. Power diode can be written in circuit using this symbol. Here we have the anode side and we have the cathode side. As you know, if we apply voltage across this diode, so the diode will be on. Or in other words, if there is current flowing inside this diode, then the diode will be on. If there is no current, or the current in the are applied in the reverse direction, then the diode will be off. And as you know that we have, this diode has a p-n junction. But of course in power diode, this p-n junction has some special characteristics. If we try to draw the curve, the characteristic curve of the diode, you will find that here is the current ID, and here we have the voltage. If the voltage applied is positive, then the current is flowing. If there is no voltage, or the voltage is negative, then there is no current. And at some point, here we have the breakdown voltage, then this will be negative. And here we said if this is plus negative, this will be in the forward bias, and if this is minus plus, it will be in the reverse bias. The power transistor is not p-n junction, is p-n-p junction or n-p-n junction. Let's say, for example, we have an IGBT here, and this IGBT is common for power as a power device. We have the gate, collector, and the emitter. First of all, let's study the behavior of this transistor. If the transistor in the forward bias, so this will act as a short circuit. If we apply positive voltage here, then the gate is on and the current is flowing in the transistor, so CE will be as a short circuit and it will be in the forward bias. Forward bias. And here G is on. If the gate is off, then this will be open circuit. Will be open circuit. But also here we have collector emitter voltage is positive, right? But in this case, the collector emitter voltage is positive, but in the reverse bias. Why reverse? Because the gate is off. So here we have full control across this transistor. When the gate is on, we have short circuit. When gate is off, we have open circuit. Okay, so this gate can control everything in this transistor. Let's draw the characteristic curve for this transistor. Here is a VCE voltage, and here we have the IC current. When the diode is off, we consider nothing happening here, open circuit. When the transistor is off, there's nothing happening here, we have 0. When the transistor is on, the gate is on, so here the current is flowing. And you know that we operating, as we said last lecture, we operating only in the saturation region, and we hope that this region is not there. And here it's at different values of gate voltage. So here is on, and this is VGE value. It can be 5 volt, 10 volt, 15 volts, no problems. Let's talk about the thyristor. The thyristor is a PN junction, and its symbols look like this. Is looking like diode, but with a gate here for triggering the voltage, and here we have the anode and the cathode. Okay, and we said that the thyristor is a PN junction. Which means we have PN junction here. Let's say this is junction 1. Here we have NP junction, so let's say this is junction 2, and here we have junction 3. Okay, we connect a gate here on this P, the second P, and here we have the anode and the cathode. For the thyristor, the operating principle is a bit different than the diode and the transistor. Here, if we apply positive voltage, so what's happening here? It should be in the forward bias. Junction 1 will be forward. Junction 3 will be forward. But junction 2 will be reversed. If we apply negative voltage on the thyristor, so what's happening? Junction 2 will be forward, and junction 1 and junction 3 will be reversed. So how to operate this? In both cases, if we apply positive voltage, there's no current flowing because we have one junction reversed. If we apply negative voltage, also there's no current because we have two junctions reversed. The solution is to trigger this using the gate signal. If we apply current on this gate, okay, what's happening on at that moment? Then junction 2 layer starts breaking and the current starts flowing in the circuit. Okay, so if we apply signal here, this junction 2, but in the case that we are in the forward bias, so we apply positive voltage and signal. So what's happening? Junction 2 layers start breaking and the current starts flowing in the circuit. So when sufficient positive signal current or pulse is applied to the gate terminal, so this will trigger the thyristor to be in the conduction state. So here if you apply positive voltage, plus minus, okay, and apply a gate current here, so all this end region and the other end region and this one will act as a big end region and the current will start flowing in the thyristor. Okay, so this will be forward. Junction 3 will be forward as well. And junction 2 will be forward. But in reality, actually, this when we apply signal, both junction 2 and junction 3 will act as big end region, and this will be, so the thyristor will be similar to this. So we have P and big end region here, so the current is flowing in the thyristor. Okay, we will call this one the operating modes here. We will call this the forward blocking mode, and here we have the reverse blocking mode, and for the third one is forward conduction mode. And this forward conduction mode occurs only if we have forward voltage and also we have current triggering the gate. If we remove the gate current or the gate voltage, what's happening for the thyristor? Will do nothing. The current will keep flowing in the thyristor and will be stopped only if we apply negative voltage on the thyristor or if the current reached to zero in the circuit. If we try to draw the characteristic curve for this thyristor, so here we have the current, voltage, Generally, Thyristor will be blocking in both directions, positive, negative, but if we apply gate signal here, so what happened to the Thyristor? Will be on, so the current is flowing in the Thyristor. And here, let's say we have the breaking voltage. And let's say here we have the latching current and the holding current. Selection of power switch is based on the following characteristics. Number one is the voltage rating. Voltage rating is the maximum voltage that the switch tolerates during the off state. When we talk about the off state, this means the switch will be acting as an open circuit. The second characteristic is the current rating. And the current rating is the maximum current that the switch tolerates during the on state. And when the on state for the switch, then this will be acting as a short circuit. So here, when this is short circuit, when this is a wire, we need to know how much current this wire can tolerate. And when this is an open circuit, we need to know how much voltage this device can tolerate. Number 3, which is very important, is the switching speed. And when we talk about the switching speed, we talk about the transition from the on state to the off state, or from the off state to the on state. And when we talk about zero switching time, this means zero switching losses. So we know in the ideal switch, the transition from one state to another, so this period of time, this will be 0 for the ideal switch. But for the real switch, we have period of time like this. So this transition is the switching speed. We hope that this transition became 0. If this is 0, then no problems and no losses. But if this transition is big, then the switching losses will be increased. The last characteristic here we have is the on-state voltage. Here we talk about the off-state voltage. Here we have on-state voltage. And you know that when the switch is on, we say this is wire, but if wire means 0 volt, but this is not the case in reality. We have small voltage. If this voltage became larger and larger, then we will face more problems. So the on-state voltage is the voltage drop across the switch during the on state. And again, if we have larger voltage here, we have more losses. If we have 0 voltage here, then there is no losses. So we need to take care about these four characteristics when we select the switch device for our power converter. When we select power semiconductor devices, we need to look into three main things, which are the voltage rating, current rating, and the frequency. Voltage, current, and the frequency. And these three parts will define the application that we will be able to use or will be able to design in power electronic systems. For example, here, if we talk about thyristors, thyristors are devices used in power electronic systems, and they can tolerate high voltage, can reach 5 kilovolts, for example. At the same time, they can tolerate high current, values such as 3000 amperes, okay? But they can operate only at low frequency, like below 700 Hertz only, like the line frequency, 50 Hertz, 60 Hertz. These values of switching, we cannot operate the thyristor at high switching frequencies. And if you talk about these applications, you'll find that thyristor is useful in power transmission systems or high voltage DC systems, right? If you talk about other devices, other thyristors, which are the gate 10 off transistor GTOs, the fully controlled thyristors, you'll find that these devices can operate at higher switching frequency, higher than the thyristor, but they can operate at a bit lower current and voltage rating, and they are useful in power transmission applications, high-speed rails, onboard power generation, and so on. Okay? Then you'll find the most common devices in power electronic systems beside the thyristors, the IGBTs, and the MOSFETs. IGBTs can be operated in many applications, like high-speed rails, onboard power chargers, electric vehicles, air conditions, and many other applications. PV systems, wind turbines, power converters, and so on. And power MOSFETs, for example, they are also common in electric vehicles applications, power supplies, microwaves, ovens, and so on. Why? You'll find that MOSFET devices can operate at high switching frequencies. So they can operate in switch mode power supplies, right? But the problem here for MOSFET, you'll find that they are not designed to tolerate high voltage levels. For IGBT, you'll find that IGBT is always optimum solution. They can operate at high enough switching frequencies, okay? They can tolerate high enough current, and also they can tolerate high enough voltage. So that's why you'll find IGBT is dominating in many applications, or they can can be used in many applications. MOSFET as well, it can be used in many applications, but you will face some restrictions if you want to operate this MOSFET for high voltage or high current. But nowadays we have many other solutions. Manufacturers are giving in new devices, are operating, are designing and manufacturing new devices. Even the MOSFET, you'll find MOSFET can operate at even higher voltage and higher current. IGBTs as well, you'll find that silicon carbide MOSFETs and gallium nitride devices, these devices can operate at higher switching frequency. And also, they can operate high voltage. They can tolerate high voltage and high current levels. So that's why nowadays you'll find that gallium nitride, for example, can be used for switch mode power supplies, for applications that need high frequency, like wireless power transfer and other things. Okay, so I'll stop here for this lecture, and in the face-to-face lecture we'll talk about the switch mode conversion, and we'll take one example. We'll see how this circuit, specific type of circuits, how it's operating, and also we'll take one example on how to calculate the switching frequency, switching time, and on and off time in the switch mode conversion system. So see you next time.